Okay, hi everyone. Can I just make sure that my slides are visible before I start?
Yeah, that's all working.
Perfect. Okay, so today I want to talk about time-resolved crystallography and the work that I've been doing, looking at different ways that we can combine data in time-resolved crystallography and how we can play that data in order to get certain advantages over just the standard approach to time-resolved crystallography. So you'll notice the title is data wrangling. So I thought, first of all, I'd like to make a logo for a horse, because when we do time resolved crystallography, we often use the first ever video that was recorded as an analog for our experiments. So what does time resolved crystallography really want to show us? I know you've been introduced to this already this weekend, but I'd like to go over it a little bit again. So really, traditionally, crystallographers have wanted to do two things, and that's look at the structure of molecules.
Hi everyone, my name is Maja and I'm a
try to elucidate a function from a static structure that we see. So we know the positions of different amino acids can tell us a lot about how a ligand might bind or about the mechanism that might occur in that active site. But what time-resolved crystallography is really aiming to do is bring dynamics into the mix. And that can actually show us mechanisms as they happen. We can see changes in structure that are necessary to occur for an enzyme to be functional, for us to lower the activation barrier of a reaction and actually get from structure to function. We have to go via dynamics. So one thing that I always like to point out is that actually the dynamics that we're seeing inside a crystal can actually be related to what we see inside a cell. Although the cell is much more complex, we find that the protein concentration in our crystals is about the same as the total protein concentration in the cell. So we are in quite a constrained environment in nature. And we do actually see that many proteins do actually retain their catalytic activity in the crystal. So in the little GIF image there, you could see the turnover of methylamine dehydrogenase. So as long as there aren't any large conformational changes that occur during catalysis, many proteins actually remain crystalline during turnover. And the timescales of the biological reactions that we're interested in are often compatible with two different types of experiment. So if we want to look at very fast structural changes, then we need to use an X-ray free electron laser. But when we're looking at slower reactions, we can really rely on synchrotron radiation to get to those time resolutions. But one thing that you may have noticed in this methylamine dehydrogenase crystal is that the color change didn't happen immediately throughout the whole crystal. There was actually a diffusion through the crystal of the substrate. And so the change that occurred in each molecule at the crystal happened at different time points in this experiment. And so if we were to probe the entire crystal at each time point, we would get multiple overlapping states in our structure. And this is very nicely depicted by this example that James Holton actually used a long time ago. So when we took the first ever video of a horse way back when, you could see that what we needed to do was to be able to capture the horse in many different states. And there was actually a bet that resulted in the capturing of this video. And the bet was that the horse never had all of its feet off the ground at the same time. And so if we had very low time resolution or a mixture of multiple states in our horse crystal, for example, what we would see would be a blurring of all the different states that we want to be able to observe. And that confuses things. In crystallography, it means that we lose information and that the density around these dynamic parts starts to disappear. But even if the density is still there for each of our states, it becomes very, very difficult to elucidate a relationship and figure out which one is which. And so what we need to be able to do is we need to be able to slice this image up into the individual time points related to each different state in order to see the structural changes that are occurring and get some information out of that for our mechanism or our structural biology. So the way that we do that is we use something called the pump probe approach. And this is a very, very traditional manner in which we can collect time resolved data. So at time 0, we pump our system, that's it. We excite it or we initiate a reaction. And then after a particular time delay, we probe the reaction using either X-rays or in spectroscopy, we can use light. And so in order to build up signal on our detector, we can do one of two things. Either we can repeat this process many, many, many times, exactly the same conditions, in order to build up the signal on the detector, or in a serial crystallographic approach, we're really limited by the amount of intensity we can get through a particular time point into our crystal. So at a synchrotron, the length of the probe determines the time resolution. That's how many photons we need to get through our crystal to produce a measurable diffraction pattern. And in the X-FEL, that's not as much of a problem, but it's still a consideration. And so what we then do is then we have to repeat the experiment by changing the change in time between the pump and the probe. And then we get a series of data sets along a reaction coordinate that show us the changes in the structure. This is very challenging for irreversible reactions because obviously we can't just repeat this over and over again on the same crystal. We can't allow it to just relax back to its starting state and try again. So what we need to do is we need to think of interesting ways that we can overcome these issues. First of all, I'd just like to have a little look at the different timescales that we're interested in, how we actually can achieve those timescales and do these pump probe experiments. So the very, very fastest things that we're interested in the proteins occur on femtosecond time resolutions. So electronic motions and bond vibrations are the very fastest things that we would be interested in seeing perhaps in time resolved crystallography, and those occur on the femtosecond time scale. Something really, really important is photoisomerization. So for the photosystems, for the photoactive yellow protein, for these things, photoisomerization occurring above the sub-picosecond timescale is very, very interesting. But there's lots that we want to see below this. So we're interested in looking at proton transfer, bond rotations, helix motions, reorganizations of water, and then we get slower and slower down into allosteric transitions and slowest enzyme steps occurring over seconds. So in order to reach our photoisomerization sort of timescales, we really need to be thinking about using an X-ray free electron laser. But the synchrotron radiation can be very, very interesting for us to look at slower things in the crystals, things that don't require such high time resolution. And so what I work on really is trying to extend the time resolution that's generally available at synchrotron. So currently, the shortest exposure time that you may be able to achieve using a third generation synchrotron is on around the millisecond or 100 microsecond time scale. And what I would like to do is using new methods, try to push that up to the nanosecond timescale, where we start to see an overlap between the X-FEL and the synchrotron. So first of all, something that's really, really important, as I mentioned before, is reaction initiation. We have to make sure that in order to be able to see changes in crystals, that we can initiate the reaction in every molecule in the crystal at the same time. So the type of reaction initiation that we do really depends on what we're looking at. It depends on our time resolution. For slow reactions on approximately millisecond timescales, we can do rapid mixing techniques. So here we take our crystals, we take our substrate, we can mix them very, very quickly. And then on a millisecond timescale, we can look at the change in state by probing using X-ray crystallography. This is okay when we're using microcrystals, and it's okay when we're around the millisecond timescale. But for anything faster than this, what we start to see is that the diffusion through the crystal becomes limiting on the time resolution that we can achieve. So for fast reactions, we often try to use a laser pulse to initiate the reaction. So we can do this in a few ways. We can do a temperature jump experiment using infrared radiation. We can rely on the inherent photosensitivity of some proteins and enzymes, although admittedly there are very few, and look at photoisomerization or direct photocleavage. But one thing that's more standard and more applicable across the range of different enzymes or proteins that we might be interested in looking at is using photocages. So here we take our substrate and we add to it a photolabile group. This prevents turnover or perhaps binding or the entrance of the ligand into the actual active orientation in the active site. And then when we remove that photocage, then the reaction can start. So although it's not as fast as photoisomerization or direct photocleavage, actually using photolysis through photocaged ligands can actually help us to access nanosecond time resolutions. So again, this is something that I'm interested in because it allows us to access those very, very fastest possible time resolutions we can achieve using a monochromatic X-ray beamline. So there are some important considerations we have to use here. What is the photolysis byproduct? Is it going to interact with the crystal? Is it going to change the pH? Is it going to affect that enzymatic reaction that we're interested in looking at? So these are all important considerations that people are now working hard to address. So, and I just wanted to show you how this experiment might work at the synchrotron. So here we have a photo of an experiment that we did on at Diamond Light Source on beamline I-24. So we use a serial crystallographic approach here for laser initiation. So we've got microcrystals that are held inside a solid chip. And then this chip is translated through the beam to all the different positions in these meshes where each one hopefully contains a crystal. So here you can see the X-rays coming out of the beamline is the red arrow. And then our very, very slightly off-axis laser is initiating the individual crystals as the X-rays probe them as they're moved into the beam. So this process is very, very fast. We use a very standard now serial crystallographic approach to collect big data sets with different time delays between our laser initiation and our X-ray probe. One thing though that's really, really important for us to do is to choose the correct time points, because often we'll have overlapping states. This is sometimes unavoidable just due to the distribution of states. So we want to be careful in that we pick time points that show us each individual step along a reaction mechanism, and we're not too blurred in our density. We can actually identify different populations of states in our density. So we want to be able to look at our data and bin it according to which state it's in. So we need to know a few things in order to be able to do this successfully. So first of all, it's really important to have prior knowledge of the solution state kinetics. I just popped this link here for people to use. So you can search for an enzyme and it can give you some information about the kinetics of lots and lots of different enzymes. It's a very useful database to use as a starting point. So once we know the solution state kinetics, we need to start thinking about what's actually happening in a crystal. So we can repeat kinetic experiments using the same conditions that we have in our crystallization solution, but still things might change. It might not be identical to what's happening in solution. So there's some ways that we can monitor changes in the crystal. We can try to follow the reaction. If there's a chromophore, as in the case of a decaging reaction, we can use UV-vis spectroscopy. And here you can see a spectra of photocaged ligand that we've used inside a protein crystal. I'll talk about this a little bit more later, so I don't want to go into too much detail. But we can see that for each different line on our spectra, we can identify that some changes have occurred. So we might want to split them according to how we split our spectroscopy measurements. Where there's no chromophore, we can use Raman spectroscopy to look for different changes in bonds forming and breaking. And there's some information that we can obtain from our crystals. So when we actually get to the data processing, we can look for different populations of states according to things like unit cell size. This can often help us to determine where there's different populations of states and where we might like to split the data up. And of course, often we have to use informed trial and error. So we use our solution state kinetics. We look to see if we can see any different populations of states in our data, and then we keep processing the data in different bin sizes in order to determine the changes that are happening and where we can see different states in the crystal. So here's one example that we work on, aspartate decarboxylase. It's got natural ligand is aspartate. We can put a coumarin photocage on it, use UV light to lyse that bond. It releases our aspartate and the enzymatic reaction occurs to produce beta-alanine. But what we saw here was that actually our photocage was being damaged by the X-ray radiation as we tried to collect even just the dark state of our crystal structure. So using UV-vis spectroscopy, we were able to split up our data set according to the dose that had been absorbed at different time points and try to find the intact photocaged ligand. Before then, we can start looking at different enzymatic states. So this experiment really now is quite simple. We use serial crystallography to collect stills from many crystals. Then using Dial's pipelines, we can very, very quickly go through peak finding and indexing and integration. Looking at the indexing and the integration statistics, we may choose to then bin our data differently according to different states, so we can cycle through that process, trying to find the optimum bins for our data. Then when we've done that, we can go and scale and truncate using aimless, and then simply just process individual time points as you would normally in a standard crystallographic data set. Oh, that's in the wrong place. So one thing that we're trying to improve is our time resolution at the synchrotron. So the time resolution is determined by the slowest of either our trigger, the electronics communication we have, timing between the pump and the probe, or most importantly for our experiments, the probe pulse width. So the probe pulse width is really limited by the signal to noise ratio of our diffraction images. So can we see those individual reflections over the background scattering from the crystal? So the signal is determined by the flux of the beam, which we can't really change, and the diffracting power of the crystal, which oftentimes is simply down to luck or how well we've optimized our crystallization conditions. The noise in our background, some is completely unavoidable. We can't avoid scatter from the sample. There's loads and loads of solution water inside our crystals. We cannot avoid scatter from the solvent inside the crystals. The scatter from the mount and the scatter from the air we can try to optimize, but again, there's a limit to how much we can remove this background. Using new detectors now, we have very little noise introduced by the detector. And we also have photon noise, shot noise, and quantum noise. So that's just the difference in the number of photons in each time we do the experiment coming out of the synchrotron. So what we want to be able to do is increase the signal to noise ratio in our diffraction images without having to increase the length of a single exposure, or without having to go to an exfil to increase the flux of the beam. So there's different ways we can do this. So in a reversible system, we can just average multiple measurements, and that's quite straightforward. But in an irreversible system, as we have with most of our protein crystallographic experiments, we need to do something else. So we can try and focus on the noise, we can try to reduce scattering, we can try to use bigger crystals, but the problem here is the bigger the crystal, the slower the initiation by diffusion, or even worse, we have the laser penetration depth. If the laser is absorbed by the crystal at some point, there's not going to be any laser left inside the crystal in order to probe the system, pump the system. So microcrystals here are actually best. We can use better detectors, or one thing, and this is what I'm working on now, is we can multiplex data points. So this is kind of similar to averaging, but it's averaging in a experimental system where we can't just repeat the same experiment over and over again. So when we multiplex data points, we record multiple time points in a single image and essentially increase the exposure time, but we can still get out our fine slices of time resolved data. So here is the basic setup for my multiplexing experiment. So we've coined this Hatrix, and the reason why we've called it Hatrix stands for Hadamard time resolved crystallography. So what we can do is we can use a pulsed beam to record a series of time points per image. So each diffraction image now is made up of 4 time points summed together. There are different ways that we can produce these pulse sequences, but they're always encoded by something called an S matrix. And this S matrix is determined by a Hadamard matrix. So this is why we call it Hadamard time resolved crystallography. So in this matrix, you'll see 1s and 0s. For each run of the experiment, we record a different number of time points. So 1 represents recording something and 0 represents we don't record that time point. So here's just a quick rundown of how this method works. We have 3 objects, and every time we measure them, produce an error. There's an uncertainty in our measurement. So what we can do is, we could weigh each object 3 times individually or multiple times individually and just take the average of that. But as we mentioned before, that's not possible with the type of experiment we're doing. So what we can do, and we actually get a better signal to noise here, is if we measure them in pairs. So we have our Hadamard matrix up at the top there. The first measurement that we take is the apple and the ball, and we record that in a vector as A plus B. The next measurement we take is the apple and the car, and that goes into our vector. And then we measure the ball and the car together. If we then multiply that vector by the inverse of the matrix, which told us which time points to measure together, we get out our individual time points, but with a smaller error. So how does this work with time resolved crystallography? Well, if we have a reflection at 3 different time points, it changes in its intensity. We then can just measure that reflection at different time points according to our Hadamard S matrix, record our multiplex data, which has the combined intensities, and then take that data once we've found our spots, once we've indexed and integrated it, and get out our individual time resolved data sets. So what we'll see is as a comparison, a traditional pump probe experiment is actually just an identity matrix. So for each run of the experiment, we increase the time delay. So we just have a diagonal of ones across the matrix. And for the minimum exposure here that we have, we can actually improve that by using our S matrix. We still need to do the same number of repeats of the experiment, but each time we're adding together different time points. And so overall, you'll see we have the same total exposure time for each run of the experiment, but using post-processing by transforming that data, we can extract our individual time points. And
right.
so
sorry to interrupt, but we're running substantially over time, so could you move to the end?
That's fine, yeah. I'll skip through. So what you can see here is that we get better signal to noise. We can find our spots. The data processing, very similar, with just a transform step there. And here we can see in different runs of the experiment, we probe different intensities. We can add it all together and get the time resolved changes in our intensities. So a number of different ways we can introduce this into the beam. And yes, so acknowledgements. First of all, I'd like to thank my PhD student, Jake Hill from the University of Bradford, and my colleagues there. Owen Pearson and Robin Owen from Diamond Light Source and Godfrey Bedard from the University of Edinburgh been exceptionally helpful, but everyone else named in this slide has been involved. So thank you.
That's great. Thank you very much, Briony.
Thank you.
Probably time for one quick question and then other questions on Slack if possible.
Yes, hello, Briony. Gérard Bricogne. I made a comment many years ago when you first published this Hadamard method that in the example you give with the weighing of objects by pairs. So what is assumed here is that when you weigh several objects at the same time, you have the same error. And these errors, that these errors are distributed. Now, if you look at the classical papers on weighing schemes, this is what is assumed. And then because the determinant of the Hadamard matrix is as big as possible with a distribution of zeros and ones, then you do get a smaller sigma. But the assumption is that any weighing of a combination of objects has the same precision, no matter how many objects you pile up on that weighing balance. So with X-ray measurements, this is not the case because they follow Poisson statistics and the errors are not normally distributed. So you probably get a gain, I agree, but it's not as good as the theory would say.
Absolutely. The analogy that I made here is actually quite trite, because what we're doing is we're taking two completely different experiments and just using it as an analogy from how we can go from traditional time resolved, traditional Hadamard experiment, put it into the time resolved thing. The thing is, what we're doing is we're not trying to improve the signal to noise ratio of our final transformed data. What we're just trying to do is improve the signal to noise ratio of our images so we can actually see those spots. So we get a balance because we've got lots and lots of different sources of error in this experiment. When the error is mostly on our detector, then we would get a much better advantage in our signal to noise ratio by doing this type of averaging. But in our experiment, as you correctly stated, we've got Poisson noise from our shot noise, and we also have random scattering from the crystal. We have all different kinds of sources of noise. So you are very correct. We're not actually looking for that increase in signal to noise ratio of our transformed data, but just to allow us to see those spots and measure intensities with more certainty.
Very neat trick anyway.
Thank you again,
Thanks.
Briony.